Hi, everyone, and welcome back for part 2 of Chapter 5 in Psych 3510. We're finishing up the chapter on measurement. In part 1, we focused on the reliability of measurement tools, of data collection. In this part 2, we're going to focus on the validity of measurement. So, reliability from part 1 was essentially situations where we want to see how consistent a measurement tool is over time, or how consistent things like different people who are making a rating on the same data or the same audio or video, how consistent are different individuals when they rate a behavior or a video or audio. So reliability is about more like consistency, whereas validity is about making sure that our measurement actually measures what it's supposed to measure, right? So we could conceive of situations where we think we're measuring one thing, but in fact we're measuring something else, something different, and we're gonna kind of see what that looks like with some examples here. There are 4 types of validity. We're going to take each of them in turn. The first is face validity. Does it look like a good measure? This is sort of almost like a subjective evaluation. Does it seem like this is a good idea? Content validity. Does your measurement capture all the aspects of the different qualities of the variable? Criterion validity. Does your measurement actually correlate with real life behaviors? Oftentimes when we collect data in the lab, there's a question about whether those data in the lab will match up with real life behaviors. We've sort of discussed this a little bit, talking about sensitive data and health behaviors, such as smoking or drinking or maybe unprotected sex. The data you collect in the lab might not match up with the criterion, with the behavior out in the real world. And then lastly, convergent and discriminant validity. This is basically about patterns of responses across similar measurement tools. So we're going to take each of these in turn and break them down and show how they're important components to the idea of measurement validity. So let's look at face and content validity first. Face validity. Does it look like what you want to measure? This is sort of your first, pass through on evaluating the validity of a measurement tool. Does it seem like this is a good idea for what we want to measure? Now, face validity is not going to be the only thing we want to satisfy, but face validity is the first place that we start. So an example of face validity, let's say that I want to measure health. That's my variable of interest. Health. Obviously, I have to operationalize that somehow with a measurement. Some measurements that might have good face validity, meaning they seem like a good idea for measuring health, are things like body fat percentage, blood pressure, cholesterol levels. Right? These all have good face validity. It feels like those would be good indicators of health. Things that I would argue have poor face validity for the variable of health are height, weight, how long it takes you to run a 10K. Right? These things are not necessarily health. Someone can be healthy if they're 5'2", and someone can be healthy if they're 6'8". Someone can be healthy if they weigh 110 pounds. Someone can be healthy if they weigh 260 pounds, right? Just at face value, the variables height and weight don't provide us a lot of insight into health, nor does how quickly you can run a 10K, right? So someone might be very slow at running a 10K because maybe they're large. They're a 6'6" NFL tight end, right? This person is probably extremely healthy. They're in peak physical shape, but they're not going to run a 10K very quickly because that's not what their body is built to do, right? They're a 6'6", 250-pound, shredded, tight end from the NFL. They're not made for distance running, and so they might look bad on a 10K, even though they're healthy, right? Which suggests that the time to run a 10K has poor face validity. There's not an obvious reason why the speed with which you can run a 10K is a good marker of health. It might be a good marker of cardiovascular health, but it's not necessarily a good marker of health in general. Second is content validity. So this is the idea that your measurement should contain all of the parts of your theory that you say it should contain. That seems difficult to conceptualize, but let me give you a nice concrete example. So in the field of psychology, there's a lot of research on personality. We find that personality is very predictive of people's day-to-day behavior, of their things like their careers, of how they function in relationships. Personality tends to be pretty stable over time and seems to be a trait of an individual. It's difficult for someone to change their personality dramatically. You might get some changes like across development, right? So from childhood to teenage years to adulthood, but it's difficult to change personality quickly. Furthermore, personality even predicts things like voting patterns in elections, whether you're going to vote as a moderate, a liberal, or a conservative. So this is a really interesting area of research in the field of psychology if we're trying to understand human behavior. The dominant theory of personality is called the 5-factor model of personality. It looks like this. We can think of these 5 factors: openness, conscientiousness, extroversion, agreeableness, and neuroticism, as sort of 5 arms of personality. And when we sort of put them all together, then we have a complete picture of someone's personality. But each arm represents its own sort of distinct thing. The theory falls apart if you don't have all 5 of these. So extroversion is sort of our classic extrovert versus introvert, right? Do you enjoy being around lots of people? Do you enjoy sort of keeping to yourself or just a small group of close friends? A nice question that I've heard that kind of explains extroversion, introversion is if you're tapped, right? If you're just tapped from the day, or you need to recharge. Do you recharge by like being social and being around people? Does that make you more invigorated? Or do you recharge by taking a step back and being alone? That's a nice way to think about whether you're where you fall along that extrovert introvert scale. And then up here we have openness to new experience. Basically, how, for lack of a better term, how adventurous are you? How willing are you to sort of step out of your comfort zone and do new things and try new things? So they're both components of personality, but they represent very different aspects of personality. And without all 5 of these, then personality theory is incomplete. So back to our point, content validity is the idea that if I'm going to measure personality, my measurement tool, my survey, the questions that I ask my participants needs to include questions that tap into all 5 of these elements of personality. If my measurement tool, if my survey only taps into 3 of them, then I don't have good content validity because I'm not getting the content I need out of my measurement. The content, the data I need to map onto the theory. And this theory of personality is a 5-part theory. So I need to be collecting data that sort of lumps into all 5 of those parts. So that's face and content validity. Those are sort of the easiest ones, I think. Criterion validity is the idea that your measurement tool, the data you collect, is actually predictive of real-world behavior. So let's imagine you own a company and you sell, I don't know, refrigerators. And you need to hire some new salespeople to sell refrigerators. Ideally, you would identify good salespeople prior to hiring them, right? That would be ideal for your corporation. You don't want to figure out 6 months later that the person you hired is bad at sales. So what could you do? You could develop a measurement tool, and let's call it an aptitude test down here on the x-axis. You develop an aptitude test and you give it to all of your salespeople, and then you correlate the aptitude test with their actual sales figures. And you can see, does my test, does my measurement tool of who's a good or bad salesperson, does it actually match up with the real world behavior? Sales. Does the aptitude test predict real world sales? And if our data looked like this graph over here on the left, then we would say that we have good criterion validity because we have a very tight relationship between the score on the aptitude test and the score in their real world sales figures. So the higher you score on the test, the more refrigerators you sell. Right? The lower you score on the test, the fewer refrigerators you sell. So this would mean that the aptitude test has good criterion validity for sales. Over here on the right, we see what data would look like for an example aptitude test that does not have good criterion validity or has lower criterion validity. Notice that the data are much more sort of scattered. They're much more random. Some people who score lower on the aptitude test do well in sales. Some people who score high on the aptitude test do poorly on sales. The relationship is not as obvious. So there's like fuzziness, right? There's noise in those data. And so we would say that that aptitude test has lower criterion validity. This is becoming an issue in higher education, especially in graduate school and even in undergraduate school as well. You have to take usually entrance exams like the SAT or the GRE in order to get into undergrad or graduate school. And some people are calling into question the criterion validity of those tests, meaning just because someone scores poorly on the SAT does not necessarily mean that they will do poorly in college. Or just because someone scores better on you than the GRE doesn't mean they're going to perform better than you in graduate school. And so we're actually seeing some movements in higher education to move away from these tests, although they still have value, and most schools still use them. But you will occasionally see schools that allow you to apply without these tests, or in particular circumstances, you can omit your scores on these sort of entrance exams. There's another way we can test for criterion validity. We can look at what's known as a known groups paradigm. So in this example, I want to validate a measurement of depression. I am a researcher who studies mental health, and I want to develop a new measurement of depression. So one thing I could do is I develop my measure, and I could give that measurement tool to people who have already been diagnosed with depression and compare it to the scores of people who we know are not depressed, right? Who have been diagnosed as not being depressed. So if I have a group of depressives and a group of non-depressives, then presumably if my depression scale, if my depression measurement tool has criterion validity, if it actually measures depression, then the group who is known to be depressed should score higher on that measurement tool than the group who we know is not depressed. Right? That makes sense. So we see here over here on the left, I have the score on my measurement on the y-axis, my depression measure, And if it's going to have good criterion validity, we would expect a group of depressed people to score higher on depression than a group of not depressed people. Now, keep in mind, this is testing my measurement tool. Nothing says that my depressed participants have to score higher, right? If these bars were equal, let's just imagine that these bars were equal, the not depressed and the depressed scored the same, it would suggest that my measurement tool isn't measuring depression. Right? It's measuring something else, or it's measuring nothing. Right? Just because I made it doesn't mean it's going to work, doesn't mean it's going to be good. I have to prove that my measurement tool is a good measurement, and this is one of the ways. We can further sort of dig into the issue by having a stratification of depression. For example, you could do this with many variables, but I could have people who are not diagnosed with depression, people with diagnosed as mild, moderate, or severe depression. And if my scale of depression is really good, right? If it's really sensitive, if it's a really excellent measure of depression, then our data should look like this. As people's diagnoses become incrementally more severe, then their scores on my measure should also become incrementally greater, right? There should be this sort of stepwise progression where my measurement mimics the real world diagnosis. So that's a known groups paradigm. I'm going out into the world and finding people who already are the thing I want to measure, and then I'm testing my new scale of measurement using them as a way of testing my tool. We can see another example of this. Let's return to our measurement of subjective well-being. So I want to measure subjective well-being. How great are things for you right now, right? What is your well-being? We can give this measurement tool to multiple groups of people, some of whom we should assume are going to score better or worse than other people. So we can see our top three groups are college students, either American, French Canadian, or Korean. We then have printing trade workers. These are just adults with jobs in printing. We have inpatients at a VA hospital, abused women, and male prison inmates. So it would be reasonable to assume that some of these groups would score more highly than others on a true good measurement of subjective well-being. Right? If I'm actually measuring well-being, then we can reasonably assume that people in prison, abused women, and veterans who are inpatients in a hospital should all score lower. And here we see they do. Here's the mean score for the samples. They, on average, score lower than our other groups of people who are either just college students or, typical working adults, right? They score, on average, much higher than our bottom three groups. So this would be good evidence for criterion validity using a known groups paradigm. Our next two issues in validity are sort of, you can think of them as the flip side of the same coin, so we're going to talk about them together. Convergent and discriminant validity. So convergent validity is the idea that if your measurement is a good measurement of some phenomena, it should converge, it should correlate with other good measures of the phenomena. And discriminant validity is the idea that if your measurement tool is a good, true measure of your phenomena, then it should correlate less, it should diverge from, it should discriminate from measurement tools that measure other phenomena, different phenomena. So let's stick with our example of depression. We develop here on our x-axis the BDI. This actually stands for the Beck Depression Inventory. It's a real measurement of depression that's very common and very well liked in the field. But we want to make sure, right? We just want to be sure that it's actually measuring depression. So it would show convergent validity if the BDI, the Beck Depression Inventory, correlated well with another measurement of depression, the CESD. I forget what that acronym stands for, but it's a second measure of depression in the field. So the BDI would have good convergent validity for measuring depression because it correlates well, right? This is a clear pattern of correlation, a pretty strong positive correlation. It correlates well with other measurements of depression. So that gives us confidence that we are also measuring depression. And then we can look at the BDI compared to a measurement of physical health problems. Now, physical health problems are perhaps a component of depression, but the phenomena of physical health problems is a separate phenomena from the BDI, from depression. And so if we are actually measuring depression, then we would expect for our measurement of depression to be less related to a measurement of physical health problems, because depression and physical health problems are separable, right? They are discriminant constructs. And so we would expect something like this, which is a much weaker correlation. Right? The pattern is not as obvious. Instead of a strong positive correlation, like we have with a second measure of depression, we have a weak positive correlation. Now, in maybe perfect discriminant validity, you would have zero correlation, right? That would make sense. But we have some positive correlation, probably because physical health problems are a potential component of depression. The more health problems you have, the more likely you are to be depressed. But we can see that these data are really messy. There's lots of variability. Again, there's lots of noise in these data. It's a weak correlation because measuring depression is different from measuring physical health problems. And because they are different, because they don't relate perfectly to each other, that gives us good confidence that we have a valid measure of depression. Whereas over here, the strong relationship gives us confidence of a good, valid measure of depression because we're comparing it to another measure of depression. So let's talk for a minute about the relationship between reliability and validity. They are not the same thing. You can have measurements that are reliable but not valid. You can have measurements that are valid but not reliable. We want both of them, right? But it does not have to be the case, right? You can have one without having the other. But in general, reliability is necessary but not sufficient for validity. So let's see what that means with this sort of 2x2 comparison thing. So let's think about accurate measurement, so valid measurement, as hitting the target. So the purpose of measurement is to hit the bullseye, right? It's to get the thing that you want to get. The further you move away from the bullseye, the less valid your measurement is. So up here in the top left, we have a valid measure, right? We're all over the bullseye. We're right where we want to be. And we are reliable because we are consistently hitting close to the bullseye. So if a measure is both reliable and valid, it hits the mark, right? It measures what it wants to measure, and it does so consistently over time. So there would be either no error or very little error in this measurement tool. Let's move to the right and look at this target in the top right. Here we are clearly inaccurate, right? We're not valid. We're trying to measure depression, but we're missing, right? We're way off up here to the top left of the target. We're missing the bullseye of depression. We're measuring something else, right? We don't know what we're measuring, but we're measuring something that's not depression. Although we're doing it reliably, right? We have a tight cluster of measurements, of darts. We are consistent in our inaccuracy. So a measurement tool that sort of conceptually looks like this would be reliable but not valid. We call that systematic error, right? There's a repeatable, producible, consistent error that's occurring. Our bottom left. So this is maybe the most difficult situation to understand, I think, because we could say that this measurement tool is accurate, is valid, because if we average all the different measurements, right? If we average all the darts, they average to the bullseye. So we're not precise, right? We don't have good reliability. Our measurements kind of jump around all over the place, but we kind of coalesce into accuracy. Now, we can't really say that we have good validity here because we still have some systematic error, right? We're missing systematically, but we're close, right? We're getting there. We might need to hone in or refine our measurement just a little bit, and then we could have a really good measurement tool. But notice that even though the darts average to a bullseye, we never actually hit the bullseye, right? We never actually have true accuracy. Just taken with multiple measurements, we sort of coalesce into a thing that looks like accuracy. We still don't want this, right? We prefer no error. But sometimes you might have to accept this situation given whatever you're measuring, right? If you're measuring something that's very difficult to get a hold of, if you're measuring sensitive information, if you're measuring something that is very time consuming to measure, you might have to settle for something that looks like this. You just need to understand the limitations of your measurement tool. And then lastly, of course, random measurement, right? We're all over the place. We're not accurate. We're not precise. We're trying to measure something, but we don't really know what we're doing, right? This is random error. There's just something crazy going on. We have a very poor measurement tool, and we're not applying it very well. So we want to make a distinction between random error and systematic error, or something we might call bias. So let's say that you actually have high blood pressure. That's the truth. That's the reality of the world. You actually have high blood pressure. Systematic error would be taking your blood pressure 3 times and it says that you're normal every time, even though you're not, right? It's an error, but it's a systematic error. It's a consistent error. Random error would be one time we say you're high, one time we say your blood pressure is low, one time we say your blood pressure is normal. There's just inconsistency, and the error is non-reproducible. In this situation, we probably prefer systematic error because we could potentially fix our measurement tool, right? If we were aware of this systematic error, we're at least consistent, right? We're at least reliable. Now, can we fine tune the measurement tool to get rid of that systematic error? We can try and at least attempt to fix the problem of systematic error. If you have random error in your measurement tool, good luck, right? Because you don't know up from down. You don't know what's happening. You don't know, is it technological error? Is it user error? Is it the measurement tool itself? You've got no idea what's going on. So random error is what we really want to avoid. We want to avoid as much error as possible. But if you had to have error, you would prefer systematic error to random error. So now we're going to talk about just a couple more finishing touches on issues of measurement. We're going to touch on measurement sensitivity. So this is about, you can think of how fine-grained of an analysis you make with a measurement. If you can think of the Goldilocks principle, right? Are we too hot? Are we too cold? Or are we just right? We want to be just right. We want to be just sensitive enough to capture fully our measurement without missing anything or without being overly complex, right? We want to be just right, just like Goldilocks. So let's say I work for Georgia State in dining services, and we're trying to collect data on people's enjoyment of the food in the GSU dining halls. That's the task I've been assigned. Come up with a way to measure enjoyment of the food at the dining hall. I could go real simple, right? I could say, one or two. You either don't like it or you like it a lot, right? Boom. Hot, cold, yes, no, black, white. That's a possible way to measure enjoyment of food at the dining hall. The problem with this sort of dichotomous measurement tool is that it's not sensitive enough, right? It only allows for responses of I hate the food or I love the food. Whereas in reality, most people are probably somewhere in the middle, but our measurement tool is not sensitive enough to capture that those smaller, more fine-grained distinctions in people's enjoyment. I could also develop a scale like this, from 1 to 100. And I could say 1 is not at all, 100 is that you enjoy it very much. From 1 to 100, how much would you say you enjoy the food? This is probably too much sensitivity, right? There's not a whole lot of reason to suggest or to think that there's a meaningful difference between someone who rates it a 65 and someone who rates it a 68, right? It's too much sensitivity. It's too many options. The difference between a 70 and a 72 is not a giant difference. Those people who rate it as a 70 and those people who rate it as a 72 probably eat the dining hall food just as much as each other, right? There's no difference between the 70 and the 72 people. So I have too much sensitivity. I've overshot my target. Whereas something that's much more reasonable might look like this. A 1 to 7, we call this a Likert scale, Likert, where a 1 is I don't like it at all. A 4 is, I kind of like it. It's not great, but it's not terrible. And a 7 is I love it. This seems very reasonable, right? There's probably a substantial difference between people who would rate it as a 1 and a 4, as well as a 4 and a 7. There's probably a difference between people who rate it as a 5 or a 6 and people who rate it as a 2 or a 3. So we have enough sensitivity to capture a broad spectrum of enjoyment, but we're not overshooting our target. We don't have too much sensitivity such that it's absolutely unnecessary. So when we're developing measurement tools, we need to think about the scale essentially of our measurement, how coarse, right, sort of like black-white dichotomous, or how sensitive 1 to 100 do we need to be. And some measurement tools will need lots of sensitivity. Some measurement tools will need very little sensitivity. And some measurement tools will need, an average amount of sensitivity. So sensitivity is a problem when you have either what we call a ceiling effect or a floor effect. So a ceiling effect occurs when the upper boundary, right, the high end of your scale is set too low such that all responses are hitting the ceiling and they can't go any higher, right? They want to go higher. People would like to answer above your ceiling, but you've set your ceiling too low and people are incapable of breaking through that ceiling because your measurement scale doesn't allow it. Your upper boundary is set too low. An example of a ceiling effect might be if I want to measure the height of the average Georgia State student. What is the average height of a Georgia State student? But I only bring a 6-foot tape measure. That's it. That's all I have. That's my measurement tool. That's my scale. I have a 6-foot tape measure, and I'm going to use it to measure the average height of Georgia State students. I'm going to have a ceiling effect, right? Because I've set my ceiling. The highest you can score is 6 feet tall. But clearly there are people taller than that, right? People taller than 6 feet exist at Georgia State. And so what I would be doing is taking everyone who's above 6 foot, 6'3", 6'4", 6'6", 6'8", and I'm basically squishing them down, and I'm only letting them have a score of 6 feet tall. I have a ceiling on my measurement tool. Clearly, that's a bad measurement, right? I'm not capturing the appropriate data. And a floor effect is just the opposite problem. So the lower boundary is set too high, leading everyone to select the lowest response. It's just the opposite. So an example of a floor effect would be, let's just kind of stick with a similar example. I want to measure the average weight of Georgia State students. How much on average do they weigh? But my scale that I use, I bring around like a bathroom scale and I measure everyone's weight, but it won't go below 150, right? So someone who weighs 120 pounds, it would register as 150. Someone who weighs 110 pounds, it would register at 150. Someone who weighs 140 pounds, it would register at 150. So the floor, right, the lowest you can score, is set too high. And so I lose the sensitivity of anyone underneath that score. So let's look at two more examples, one each of ceiling and floor effect, and then that'll be it for this part 2. So if I asked you, how many hours did you sleep last night? Please choose one of these 3 options. Did you sleep 1 to 2 hours? Did you sleep 3 to 4 hours? Or did you sleep 5 or more hours? This question has a low ceiling because I'm losing the opportunity to record the sensitivity of anyone above 5 hours, right? Anything above 5 hours, I've lowered the ceiling to just 5 plus. Because clearly there are people who are going to sleep 5 to 6, 7 to 8, 9 to 10, right? It's going to happen. There are those people exist in the world, but I miss them. I lose their data because I'm essentially capping a limit on the ceiling of how high they can score, right? They can only get to 5 plus. And so my data are going to be garbage, right? Even if I do all the statistics right, even if I have good research methods, because I have screwed up this measurement tool, the data are useless. And here's an example for a floor effect. What is your annual income? And so we say, okay, we'll just take some standard. Sorry, there's a B that almost got me. Let's just take some standard chunk of income. Let's say $100,000, and that will be our increment. So please choose one of these three options. Do you make $0 to $100,000 a year? Do you make 100 to 200? Do you make 200 to 300? Do you make 300 to 400? So on and so forth. So this question has a high floor. Why? Because someone who makes zero income, right, who makes no money, is going to be put in the same category as someone who makes $100,000 a year. And so it does not provide enough sensitivity on that low end, particularly for this question, income, because most people are going to fall into this category, right? The vast majority of Americans are going to make between $0 and $100,000 a year. I don't know exactly what the data are, but I mean, I'd assume it's something like, 80% of people. I wouldn't be surprised if 80% of people make between $0 and $100,000 a year. And so you're taking those 80% of people and you're just making them all look the same, right? They all get the same category because your measurement is insensitive because of a floor effect. All right. Thanks, everybody. That's the end of chapter 5 on measurement. Thanks for watching, and I will see you next time.